Not renewing certificates. Hello everyone. Okay, here we go. New hairstyle. Shorter again. Or was it like no? I didn't stream since last time. Some people maybe saw me already on. Oh damn! I forgot my power supply downstairs, but I think I have enough USB cables here. All right, hello everyone. Sorry for the slight delay. I need to somehow improve stuff. Hello Sonic, hello TMK, hello Wagon Loads, hello Dutch, hello Johnny, and the Sheepu, hello. Are you all curious about the latest state of my Ultra cluster? Yeah, we can talk about that. Now I'm feeling very confident right now. It's delayed, but it's still. I don't see any roadblocks yet. The funds are still substantial, so it might be possible to finish that. I bought a new. We have. What was the things that we worked on last time? Was it the power supply? Did we research that a little bit? Yeah, we can. I have decided I bought all the power supplies of Mauser. It's still not enough. TME has some more, but they're like $4 more expensive. So I will get the rest from them. And are you hearing me by any chance? Yes. Yeah, no, you're not. Okay, you can hear me. No, you've never been. You just jinxed it before. All right, so here we go. I show you. I show you. Oh yeah, power connectors. We had talked about. Oh, Jason controlled. Yeah, why don't you take the DP100? You can control it from the browser. You don't need to reinvent the wheel like I do all the time. Look at that. You pinxed it. What? Ah, yeah, you pinxed it with the pink font. What? Oh, wait. Oh, no. Now this side is 2 rows below of this. I don't know if I can accept that. I can array that again. But I would need to delete those and copy that one again. Don't cross the beams. Look at that. Look what I decided on. Okay. I ordered also cables. This will be the XT60 connectors, not the XT30. I don't know what the last state was. XT60 are too chunky for this current, so for 30 amps should be doable with XT30 as well. Yes, beefy. But they are more common than the other ones, so I will just take those, sort them on, and be good. As well as the cables. I think I got the cables as well. And we found some cool heat sinks. Your pedelec approves? XT60? Yeah. It's enough current to drive a bike, so it will be enough current. No, wait. Bike is only like 1000 watt, not 3000. But we distribute it here, so look at that. It's plenty. Conveniently, I didn't know when I designed it. I put all the power just so it's in the center of the card to one end of the PCI Express connector, and look at that. Ah, beautiful. It's all just one thick plane, so no worries about the current here. And also the LED, that will be just a thick trace or a pour as well. And then we have some signal wires. We can put the VLED since the current requirement for that is quite low. Let me check that. Here, I need to check so I don't jinx myself. First, the browser windows I didn't clean up, didn't have time. Or else I just had like 2 really juicy burgers. It was amazing. That's why I'm late. We just returned from, I was swimming 1 kilometer today. And then we went shopping. I got fresh minced meat and made some burgers. Now you get hungry. Stickers not activated. What? Huh? Let me check. Am I demonetized? No, it's monetized. I don't know. What is this? Add stream maker. What is an ad? What is... Makers appear in the video editor. What? Oh no, what just appeared? Spare ribs? Oh, that sounds great. I think monetization should be on. I don't know. Phew. Hello, welcome by the way, and hello Kasper. Oh, Kasper, you will be of great help today. I think did you who posted the Tang Nano Tang Prima 25K footprints. So chat. Oh, what? Here we go. 27 SAK. Let's put it in the embezzlement fund. Embezzlement fund is the current one. Oh, you know what? I tell you that we almost got the excavator, a discount of $500 on the excavator. Almost. 69.27. Okay, so how do I add? That's 7696. Oh, you wanted to invert it. Nice job. Okay. All right, here I show you. Ten percent of 5,000 is $500. And I show you yeah, but the issue is, yeah, I could have one with roof. Look at that. Turmbaumarkt. Zipper is a Austrian brand. Let's take a look. Oh! Meiningen. Okay, because it was sold out. But we get one in Meiningen. How do I get one in Bebra? Maybe I can wait. Oh, really? Like, oh yes, that's good. Yeah, I'm looking forward. Look at what we will solder. I mean, look at that. I will hand solder all of that on stream probably. I don't know. Maybe at least one set or something. I have to XT60 connectors. And there is no thermal relief. Look at that. We have to heat up all this copper. Yeah. And you can always replace the handle and stuff. Wait, what is this? Hate it when they do that. Okay, let's do components. Is this component? Oh no. What did I do? Not polygon fill. That's the component. Yeah, designator is shown. Okay, so let's select, find similar objects, show designator, same, ok, and then disable the designator. Boop. Now it's hidden. Hey ITT. It looks cool, doesn't it? Huge. JSON enabled excavator. Hey, Riado Voy. What a name. It seems like Twitch is more creative with the names. They're always barely pronounceable. All right, so we got, so decided on XT60 connectors. The math on that you can find here, especially from the measurements. So what I calculated, the maximum current from the data sheet would be 5 amps, and I am connecting 4, hey Yumbo, 4 of the power supplies, for, oh, Delt, hello, like encoder, no, it's a base for the ultra cluster. We will plug in 128 PCBs with 512 MCUs each. AI agent. Yeah, we'll electrify maybe the excavator at some point, because like the motors are quite like weak and whatever, and since it's running just in a constant, more or less constant, or however demanding, it's running just a pump, isn't it? Like they have like the propulsion and everything works with hydraulic pump. You can just direct the pressure or something with the lever. So I think the tech is quite easy. All right, so we calculated, this is the requirement for VCC0, which is the main current. As you can see, even the LEDs are like only 1/4 of that. It's excavator is still gas, like they're all gas, but we can then just convert it. Why not? And then if we, what I measured is 4.8 more or less instead of 5.2, and that was completely with everything, even with the LEDs combined. And I think that what was the amps? We can check on the camera here live, since we have one of the rows. We'll rent an Atlas. Yeah, I want to own one. Yeah, probably. All right. Yeah, if I can get really this. Why don't I see anything? My camera is. Oh, I turned it off. Why is the card full? Did I record anything? Yeah. All right. Let me show. Oh, Boston that Atlas. All right. Jet controlled excavator. Yeah, maybe we will do that. If we can get like electric replace every part of that. Okay, so if we let's turn on our power supply. Okay, so this is the current that we one row of MCUs, 270 milliamps more or less. And if we add the LEDs, resub, thank you, Johnny. We draw more or less 300 milliwatts if the stars are gone. So it's like 400 milliamps right now, but 330. but this is cycling the colors, so it's not like never like all the channels at the same time. If we drive it at maximum, it will be 1 amp. Not 1 amp, 100 milliamps. Ultra cluster of MCU, yes. So, and that math is more or less right, because we have 1 milliamps per channel. This is 32 LEDs. Right now one is off because there is the different code on that. So the math is perfect on the LEDs, and on the MCU we get like 270. If we let me remove that. The LEDs are off, the MCUs are on. 270, and then if we multiply what we calculated, 270, let's say this is, I would round up to 300, but we have 16 rows on one blade. It's 4.3, and then yeah, I calculate like with half an amp more. That's basically like 4.8 amps, and let's round it up to 5. Then if we, or it's like 19 amps here, and at the XT60, 12 AVG, AWG gauge should be enough for 20 amps. If anyone says something different, I mean, it's Chinesium wire gauge, so I'm not sure about that. I ordered a bunch of wires. No, I think, did I order the wires already? Oh yeah, I don't know what I ordered. Let's check that. I ordered at AliExpress quite a lot of stuff recently. Yes, for 80 bucks. But I think I must order even more XT60 connectors. Here we go. 40 centimeters, 12 gauge. Percent. No, it's active right now, so I could just go there and buy it right now. But I need like to get it shipped to my place, so I will ask at Bebra maybe. Yeah, so quite cheap, like 250, but we need like, look at that thing here. We drive 4 blades from one connector. That's 20 amps. I hope the copper is enough here. It's at least on the other side of the PCB. If we look at it, like, no, it won't. It is only like, okay, so they will go on the back side of that. By the way, the connectors arrived today from LCAC. So here, these are. Oh, I can just use the camera here. Whoopa! Here we go. So these are ×4, PCI Express ×4. Where's the card? I can show you simple ×1 card. Oh, this the chaos. I was searching my headphones today. So everything is very chaotic. I should really not lose my 10 FPGAs. No, it can do more. Not only driving the LEDs, but the LEDs as a substantial feature for the presentation. Wait, I had a box full of cards here, I think. Where is it? Yeah. So yeah, PCI Express times 1. It's plugging in like that, so there's plenty more, and they are just short enough so everything we can fit in a circle of this diameter, them right next to each other with a clearance of 1 millimeter. So that will be that will be a thing. Look at that. Quite some pins to solder. Is there a key code for flipping? And that's not all the pins, huh? There will be more. We have like different power levels that we need to place there as well. All right, so power supply design. Connector here. I don't have the level yet for that. I'll show you maybe quad blades. Yeah, this is, I don't think. This is the connector. That's a 4-blade configuration. What I didn't. Yes, Yombo, you are right. It's price-wise the best thing to do. For the power, it's beefy. You can solder it to a PCB, whatever. It's the solution. And you get the cables cheap. As you can see, we got like if we compare it, that's even cheaper than the PC cables, because the standards are odd. Like we try to get like the ATX here, whatever. What is this? Yeah, this is the serial ATA cable. They have not enough current. I would need like a ton of those, and in the end, they're at least as expensive as XT60, and they can carry 30 amps or even more, up to 60. The connector at least up to 60, but there is no like 8 gauge or 10 gauge wire that you can get off AliExpress like that. And we have like the length that we like. How many did I order? How many did I order? I don't know how many I ordered. 19 bucks. I need more because apparently I will use, I mean, I have some here, but they're probably, yeah, there are not many. Like 10 maybe. It's still here. You can always get them like locally because that's like a typical hobby product. So I don't need necessarily to get this from China. Is this all I ordered? Huh? Where's the other stuff? Oh, I didn't place the order yet for the other stuff. I have it in my cart. Let's not talk about this thing. This is for future. You can screenshot it. Here, that was your chance. And then, yeah, I don't know yet how many I need of those. They are quite pricey, so it's a quite high price point. But look at the cooling solution. I need an active cooling solution for my PSUs, and it will be at least 32 power supplies. So yeah, $100 just for, and this is quite cheap. Like they can dissipate 10 watts. These cooling fans. I think I will take the beefier one. This is just for testing. What is this? This is old now. Yeah, I think I have more in. There's like, is there a choice pipeline? Yeah, here. This here. Look at those here. These are even cheaper, so I might just buy those here. This is for test, and look at that. RGB heat pipe cooling fan for CPU for 8 by. I'm just curious. I just put it in my basket out of curiosity. And this one is more fancy, $7. Hey Omar, thanks for following that long. So yeah, that's Noctua is 100. Yeah, and this is $8. So do I have? No, this is mirrors, old projects, old projects. Yeah, fixing my lens. Should order that. Yeah. So this is the AliExpress thing, but let me check what my Mauser order does, because can you believe that Mauser was cheaper than anything else? Wait, let me add this to basket so I won't lose. Okay. I need to check that I don't get doxed here. Oh no. Wrong browser. So power supplies. Power surprise. Yeah. Ah, yeah. That was a dox. Oh, yeah. Dudes and dudettes. Look at that. I bought, you know, that when we talked about the jumper wires, I bought these jumper wires. I bought them. We'll see how they are. We will test it. Since I ordered at Mauser, I had them in my basket. Look at that. $300. And I took all of them. Stock is 0. I need more. I need at least 32. But DC to DC, 0.7 to 4 V out. And yeah, the price is unmatched. Anywhere else it's $14. So I probably just bought off their old stock that was running out of like time or something, because you like to use them up, or I don't know. Here are the specs. We will run them at more or less, we could run them at 30 amps. Yeah, we will run them at 100 watts. Quite simple. We have a trim resistor. I will put a potty there so we can adjust the voltage a little bit and reduce just leakage, waste current, because we can run the MCUs at 2 volts or something. We just need like to stack the chain like in a different way. Yeah, that's the V out. Then there is like, we can use, we can turn it on and off digitally, which is cool, because then we can power it up slowly, everything. Cat ear, what? Who ordered it? A BGA-esque, yes, it needs that because it's SMD, and then they need like to output that current. As you can see here, current limited, no damage, circuit, short circuit protected, everything. Oh, car battery. Yes, we could jumper cables, like car jumper cables. We could run it from a 12-volt battery. We would just attach it to a car battery, and then it will power up, probably drain the thing within, what is it, 50 amp hours. So it will be, yeah, running for half a day. So 30 amps, input, startup threshold, blah, 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 blah. Nobody's interested in that. Efficiency. Here, it's interesting because the use case is for FPGAs, CPUs, whatever. 94% at 30 amps. 94, but we'll see the graph is quite interesting. That's why I decided I rather get more and have less problems with heat and everything with the current. 40 degrees. Oh yeah, I have no clue about that stuff. Yeah, at 40 degrees, oh, it run for 8 million hours. Okay. 400 kilohertz is not that fast switching frequency, but all right. Okay. Let's check. That's internal. They have everything covered. So this is optional, I believe. Yeah. Recommended application. You just need a transistor to pull it down. If you want to switch it. Oh wait, it's off state. Yeah, it might be off by default. So we will do that and add basically a pin. So we can turn it off and on. Something that we can design. Maybe I will stream more often so we can do some of the designs together. It will be a bit tedious to get the footprint made first, but I might be fast enough for that. Regulator, okay, blah blah blah. This is interesting. Power good. Look at that. So connect to other converters on off terminal, etc. So you could daisy chain or what? Power good. Or just sensing. Yeah, we could sense it or do whatever. Okay, this is interesting. First, if you look at that, you're shocked. Oh, efficiency 85% if we have Vin of 12 volts. But then this is the graph for output voltage of 0.7 volts. So you can run it really low, like super fast CPUs, GPUs, or whatever. They run at core voltage, which is that low, most probably. I don't know. Load regulation, whatever, switching frequencies, some glitches. For LEDs, yes. 1.8 volts, more common core voltage. We get already, this is interesting, the graph, like if you don't draw any current, it's not efficient. It's like below 70%, whatever. But if you draw, let's say 20 amps, that's what we aiming for. It's already at 90, I would say 92%. The optimum is around 15. So we are in this range, which is quite a sweet spot for the efficiency. Or the sweet spot would be between 12 and 15. I think we calculated 4.3 times 4 is 16, 17. So right in the middle of this one here. This is where the typical current consumption will be for that. And this is 1.8 volts. Then let's go 2.5 volts. Looks better and better. And here, ladies and gentlemen, we have a winner. Look at that thing, 95%. So let's run it at 20. Connect all of the switch on off inputs. Yes, PCF. Okay, let me get that part number. PCF is, I don't want to switch them all at once. I want to switch them on sequentially so I can boot it up slowly and what is that? Provide expansion. Oh yeah, all right. typical GPIO expansion. Yeah, I could use the shift register for that. I don't mind. Or the FPGA. This is nice to have. We will probably just take consider using. Yeah, but you tease me with these things which might play a role with our new development here. All right, so we're planning to run it about like a good 66% of maximum current, which is 20 amps here. That will reach at 3.3 volts. We will, if we run it lower, it will be probably 94. 2.5. This is also the voltage that we can run the LEDs at. So, but then it is 20 times 20 amps time 3.3. So it will Alien Tech Power Supply. Is it cool? Do you like it? Maruon. So we have 3 times, what is it, 20? That's 66. 66. Yeah, 16. Yeah. The expander. Yeah, we will run it. Let's say maximum. I think like the maximum will be like 100 watts that we run them at. And at 95% efficiency roundabout, like the rough estimate, we have like 5 watts of power dissipation that we need to take care of. And 5 watts is a lot. Peeps, 5 watts is more than I like. And this is how the thing looks like. This is quite interesting. I like the footprint. Okay, so this is only 8 millimeters tall, so we can place one of those heat sinks on top of that here, this thing, and since it's active cooled, running from 12 volts DC, sweet, we can just run it from the input power for our converter. It's just an JST connector there. Hey Ray. And we have, I have somewhere the measurements for the distance of those pins, but I'm not sure. Yeah, you know, that's like the plastic pins. Yeah, if they are long enough, I hope they're long enough to basically place on top of the inductor, and I hope that's a good thing. I will leave place on the bottom of the PCB, so I will put a pad on the inductor and put the fan on top of that. So where's the data sheet? Yeah, yeah, balancing that huge 5 centimeter heatsink on top of that 10 by 10 millimeter thing will be interesting. Yeah, this is how it looks like. That's not like a lot of different pins. Look at the board here. They even provide a good design. Vias, this is ground, all ground. So probably we will be able even to put the heatsink on the bottom. So I will place all the through hole connectors far away enough that the heatsink, if we put it on this side of the PCB, they wouldn't interfere, and we have like a good connection. But other than that, look at that, how the dev board looks like. It's just SMD caps. I think it's 800. Was it? Yeah. C3 to C10. Okay, look at that. C3, we have 8 populated 100 microfarads. So we have 800 microfarad 6.3 volt outputs caps, and only two 22 microfarad input caps. So that's very convenient. We can use the caps. I hope I get them. Wait, let me check that part number. If we get the originals or they're Murata. They want to upsell me with some more Murata stuff. Murata. What's the cost? What's the cost of this capacitor? 62 cents? What? No way. I will place something else there. Yeah. Chip cheap, caps expensive. Yeah. If you place 8 of those at volume of 500, they cost 20 cents. So you have 4 euros for no wait. 8 times no 1.6 dollars just for the caps, output caps. Nah. No, my friend, I might place an actual electrolytic cap there. Not sure if it's optimized for that. We should 0 ohm resistor. Is there? Oh, there is a resistor for 0 ohm. R1. Here, V out is sense, and R13. No, R13. Okay, we have sense minus and sense plus. Okay, 0 ohm resistors. Why do they need to be so big? Low resistance, yeah. NGL sim surfing. Hey? Oh. Agree, okay. Huh? How does that work? Ah, alright. What was 6.3? Huh? What do I do here? Part number search. Okay, let's check the part number if we can. Let's get that, and then we can maybe. Can we? Yeah, but they have like. Here we go. So we have all the parameters here. Plus my tolerance is 20%. Chip size. 125 degrees C rated voltage. Yeah, it doesn't say anything. Okay, let's check LCSC. Let's see how well we can get. Okay. Capacitors. Yeah. I don't know if they are special ESR. They probably say that. Can we get like a where did we find it? Oh, ESR graphs for. Okay, let me check that again. Datasheet. I mean. But they only use. Do they have like? Can you use like different brands there? Well, where are the specs for this cap? Test voltage 250 of the rated voltage. Interesting. Why shouldn't we use like, okay, electrolytics are always, oof. It's probably for the low profile. If you have like a PCB, you can do it in low profile. They probably show off with that sizable caps. Okay, let's check out chip resistors. Samsung, yeah, we can get them. There are. We can get also good ones from here. So microfarads, 100. Air is thin there. Let's check what they have. What is this? Plus 20, plus minus. I don't know what this means. Minus 20, plus 80. No. Yeah. Oh wait, plus 80 is good. Minus 20 plus 80 means the capacitance can be a lot higher, which is cool. I guess. Voltage rating, we need at least 6 point whatever. Yeah, these will be way too Asian brand. No, here we go. 5 cents. Okay. In stock also, and then Samsung Murata 21. So what do I take? Samsung or Murata? Same specs. It looks like it's the same specs. Oh, they are bigger. That's the issue. Murata, they show off with small size. I don't need small size. I need small price. Let's raise the price from 5. Yeah. We can have, okay, that's Asian brand. What is CCTC? Is this a reputable brand? No. You know what? Okay, we can get them for 8 cents from Murata themselves. Let me check if that one will be alright. Yeah, how do we do that tool here, that comparison tool? That, oh no, wait. Where are we? We are lost. Ah. Yeah, no, I'm doxing myself now. Did we use it here somewhere? This calculator? No. I lost it. Anyways, we can order them. I guess the Samsung ones will be alright for 5 cents. 100 N, nice. Okay, let's check the data sheet for the Samsung. If we spot something that's 200 Bible thumb, what is, what? All right, so this is the size that we want. Dimensions, they vary a little. Wait, what? No, I think this is a wrong voltage rating. Let me check that. Oh no, it's 6 point. Yeah, X5R. All right, you know what? I love that option here. Did I add it to my cart already? No, that's an amphenol connector. Okay, add them. What's the sprite? Okay, we have 8 times 32 and even more like 40 of those. Let's say 50, that's 400 at least, so we can buy 500. We should use 500 here. Oh wait, no, here, Samsung, not the Asian brand. How they stack it? 300 plus. Yeah, let's take 400 then. Or 500. Let's do that. 19 bucks. Okay. Yes, they are lower. It's 8 millimeters. It's not a chip. It's actually a combined SMD assembly with a big chunky. Not that one. Oh no! I'm doxing my plans. I'm doxing. Don't look up this part. Don't look it up. Everything doxed. What? No, not doxing it. Unobtainium, these high-speed ADCs. They're like 20 bucks each at least. But these are the only options, I can tell you that fulfill the requirements that I desire. We need to beat NVIDIA, so unfortunately I have to use that. Where's the I lost the window. Where's my Mauser datasheet window? It's so weird, it's gone. Huh? Found the mini bugger again. I have too many windows open. Still have the oh wait, no. Oh wait, I might have the thing also here open in this one. Yeah. No, wait. Docs my socks. Let's open it again. I think this was that was the one, yeah. We just open it over and over again until we are done. This is wrong. TME has the wrong specs. They say it's constant 4 volts out, but it's not. It's somehow. Why is it not loading? Here we go. No data sheet. Toll. Here is the data sheet. No, this is a different one. I think this is the one. Yeah. No, this is also a different one. Yeah, all the wrong ones. Alexa has nothing to say here. I have none of the spying assistants. Oh, that's the okay. Order confirmation. So it has to be. No. Here it is. Yeah, that's the one. Can close that. So it looks like like that. Not bottom soldered. It comes in a tape. It's so crazy. It is small. It's like really tiny. This thing. Okay, you can see. I don't know. They don't show the profile, but basically, yeah, it's 8.3 millimeters, and the caps are at max like probably more like this size. Cool thing. Pin 1 at the back side. Interesting. All right, here's pin 1, so it's flipped in this direction. Yeah, it's quite easy. I mean, this is only ground, 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 and we have in, out, or out, in, I don't know, and then we have like the sense pins and stuff here. So they're just copied, so you can, yeah, sense, trim, whatever. And we will make it trimmable. This is really cool. I'm looking forward to it. I hope it will arrive soon. Let me check. Maybe I have like order confirmation, order tracking. It should be FedEx, so I guess it will be 4 days total from US. Oh shit, the order is the wrong email address. Anyways, counts. Come on. Order history. There. Tracking. Huh? On the way. Arrive at FedEx location Riossi Charles de Gaulle. Oh, it's in France already. All right. So I guess it will be taking another day to Germany, and then it's quite close. If it's not in coming from. Oh, we will have the device here, so we can physically test it with our power supply and everything, measure it, see where the heat is coming from when we run it with a load. So we will do this power supply design, and heat sinks won't arrive, but we have different heat sinks here. We can test everything. Mwah. Variable? No, it's only up to. There are different ones that have a better range, but 30 amps you can trim it up. What is the max? I think 4.7 or something. No, what is the output? Yeah, 4 volts, 0.7 to 4 volts. So it's really only meant for high currents at low voltages. But there are different Murata supplies which are quite capable as well. If you look at that, I can show you the window here. That was basically my search. Oh yeah, there are even ones that are even lower output. Input voltage. No, wait, output 5. Okay, you can't see that. That's what on this side here. Scroll that for you. Output voltage channel. It's very specialized. 5 volts, 5 volts, 5 volts. But if you need like a high current supply, it's like worth it, I believe. I mean, if I pay $10 for that, instead of putting like 31 amp in converters on one PCB, it's the same price in the end. And I hope it is a good quality product. What is the output voltage? There are some even that are programmable where you can set them, I think, digitally, the voltage. That would be a good thing. Yeah, you need probably to search the... Yeah, this is just to my filter to my specs. Yeah, that's cool. All right. That is that. I need to drink. My throat is quite dry. No booster today. I haven't been to the store that has the booster. That was this thing. So let's sketch up. Paint. We can test it. I guess the PCB will look like top view. Top view of the PCBs will be like that. Let's assume it's like that. Then we have the heatsink on top of that, active cooled with the fans. We have fan spin, my friends. With some heatsink. Then we have it is what it is. It's FedEx. Then the side profile will probably look like that. So we have the heatsink here. It's balancing on this converter like that, and we have the pins here. Let's hope that works. And then we have on the other side, since this will be outside, boop, 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 boop. That's the XT60 connector. And then we need some splitter cables. I think that's a 4-pin or whatever. 12 volts in. That's the 3.3 or whatever, 3.0 volts. Then we have the trim. I will use one of those. They can't, the blue ones, they can't be easily easily bumped and have like fault or whatever. Then we have connector probably, okay, these connectors, oh, this is wrong. This will be all out of the profile here. So, trimmer, and then also a little connector for power goods and stuff like that. So we have PG. Oh, really? Oh, really? Huh. Why do you think they will be cancelled? Why are they restricted? This is interesting. I mean, I can get them from elsewhere, but there are not many sources. They are not unobtainable in Europe currently, I think. There is... Oh, really? Tell me about it. So what's the issue? Oh, really? Okay. Hmm. Where are you located? Oh, wait. Setuna. The name rings a bell. Where do I know you from? Germany, yeah. LCSC? Alright, I will. I saw them even cheaper on AliExpress, but I... Ah, okay. Ah, yeah, right. Yeah, yeah, now I know. Wait, but wasn't that... No, is it YouTube as well? I thought it was Twitch. Ah, now I doxed things. But a good tip to not order those things from the where are they? I lost the window. Anyways, yeah, we need to find out. So as soon as these things arrive, like this DC to DC converters, we need to find out if with a thermal camera, if this if we can dissipate the heat from here or put it on the other side and dissipate it from there. Like let's imagine the heatsink is sitting just with a lot of vias on top of the board and the thing is on the bottom. So I don't know what the right design is right now. We can test that, or we can design the board so it looks the same way. Yeah, no, they are right. They're just 1 or 2 days delayed. That's not the bottleneck right now from shipping. I tell you what the bottleneck is, and this is JLC. I don't know why it takes so long. I mean, the boards are like, look at that. It's stuck for 1 day in via filling epoxy copper paste, whatever. It's like, why is it taking so long? Isn't it like 25th already? I mean, it's night at the yeah. They start at 4 o'clock again. So I guess anything else will happen. The plating takes half a day. Okay, then everything is might be straightforward, but it's taking them so long to manufacture those boards. Okay, we are placed. They started. I placed the order way earlier, and then the review process was quite long. It took them like days and days. And I placed the order. Maybe we can see that. Uh, 18th. On the 18th, then there was like some review process and stuff didn't work out and whatnot. And now we have already 25th, and the boards. DC to Z converter is restricted. Mine are shipped. Yeah, they're still drunk from Chinese New Year. They even show that there might be delays, but on top of that, when these boards are finished, they need to be placed. Like, we have several thousand components that need to be placed. So I don't know when I will receive these boards. Earliest next week. Next week, like end of next week, maybe. If DHL doesn't like keep them forever or whatever. What was what is the Satuna? What was the exact part that you ordered? Was it an DAC, or was it an ADC, or what was it analog devices? I mean, I ordered the DC converters. Okay, ADL. I'm wondering if I have. That's RF mixer. Oh, yeah. Okay. But this is something else than a DC converter. RF mixer is basically what you can use for like probably drones, drone manufacturing. Ah. You know what? Maybe I should just try. If they cancel it, that's all right. I can order somewhere else. I'm just wondering. I'm really curious if it's what the issue might be. Weird. Or you are flagged. Yeah. So look at that. I ordered these boards 5 days later. That's my test device. I think I finished it on Friday, and yeah, there it's already through completely. Soda mask is next. So, and I only took like Euro packets, so these will be certainly arriving before the blades, which I placed like 5 days earlier. I'm not sure why it's stuck there. Super slow. But this is also only a 4 layer board, so this is a 6 layer whatever impedance, so what that matched super PCB. that's that's why look at that price, pips. Look at the price. 400 bucks for 4 boards. There will be only 4 PCBs. I paid a total of, no, that's the total. No, wait. Oh, Mauser. It's also an RF mixer. So yeah, I guess RF, because you can for they I mean, this is now flagging welcome FBI to the chat, or CIA or whoever, national security. We are talking about export restrictions for RF components, and my guess would be that basically for drone jamming or spy drone localization, for warfare and stuff like that. National security, guys. Yeah. So I guess that might be anything that has to do with RF that you can use for that purpose will probably be restricted, because otherwise, if we the deck that the deck that I want to order uh, from analog devices, it's internally just an R2R ladder or something. They would need like to restrict resistor networks and op amps as well. Yeah, I will order it. Let's try it. Okay, I will order it right now. Um, Let me get you off. What was the part number again? Damn it! Because they are so pricey. Like that's $90 for only like three of the parts. So when I built it, the device, you can get them for $10 from AliExpress, probably refurbished. But I don't trust the seller. I really want to have it. Yeah, I think that. Oh yeah, you got that one. It's cool, isn't it? The chip is amazing. But they don't make it. Sorry. Where I live, yeah. I'm only worried. Should I what? There is the difference between, look at that, $32 versus 36. So why not industry grade? This is consumer grade. This is industry grade. I want to see the difference on that data sheet. What is the wait ID? No, yeah, we can find it. DFGA, you're really upset with them. Temp ratings? Yeah, we don't need high temp ratings. I'm thinking if they have like a sorting of the sweet spot, because you can get some noise on the least significant bits. This is a really high precision device. It's 16-bit ADC with quite fast sampling rate. DAC, not ADC, sorry. DAC, no. Too much text. Oh wow, what do I do here? It's the reference design. Yeah, we need to be very careful with those chips. If I kill one, that will be expensive and take a long time. What is this all this crap? What is it for? This is to humiliate Nvidia. That's what it's for. We will humiliate. That's why we need 3 of those. Differential pair. Ah, 6.8 CG. 100 degrees. For turning digital values in analog again. Offset error. Oh, was it? Where? Did I miss it? Yeah, but it doesn't say. This is still for the ultra cluster. See at the end of the part number. Yeah, I know. No, wait. Huh? Keep going up. Oh, yeah. Consumer industry grade. 70 minus 40. Yeah, we are fine. If we can, yeah, that's totally fine. All right. So let's get. Maybe I should get 10 so to get a better price. Let's get 3 first. $100? Damn it. Yeah, I think DFGA, I will pass the free shipping cost here. All right. Crazy. Okay. DigiKey is more expensive, I think. DigiKey, or they don't have it in stock. There is, like, you can't get this part anywhere. Yeah, I know it. It is. You can't get them. I wanted to order samples, but they don't have. Analog Devices doesn't have them on stock. Oh no, this is not the right one. DigiKey. Okay, let me check DigiKey. Yeah, development board for $75. Arrow. Not found. This is unobtainium, peeps. Elditz. No, that's just the data sheet. Farnell. Now we get only like a similar chip on Farnell. There's no way we can get this. Okay, so let me view the baskets. And then we will just order it. Oh. Back ordered? What does that mean, back ordered? There are back, and you will be able to make additional selections during checkout. So they're not available. What? Yeah. What? They say it's... Oh. Oh no. They expected... Look at that. Expected at... Oh, damn it. Non-stocked. Nah, this is not... We can get this thing from here. Oh, wait. No, reel. We can get a whole reel. Lead time 24 weeks, yeah. Yeah, we'll just wait for them to arrive. There is no... Oh, there's also reel here. No, reel is 2000. Yeah, I will get them from LCSC. You got me. I wanted to, but I don't wait like indefinite. Look at that. Yeah, almost April. But look at that. Oh wait, this is... No, it's not April. This is not April. This is 5th of January. Is this American style? Please give me ISO format. Let's check Deutsch. See if they change the date display here as well. 6.4. That was 1.5. Yeah, you know what? If they expect it, I can still order it then. Alright? Yeah. It says it's expected at in 2 weeks, but then we can order it. This is also the last part that we will make on that. So I can tell you what the thing is that I need that for. Yeah, I know. But I don't order something in advance. Why should I? I can order it. Usually, if they say expected, it will be delayed. But I don't want to get delayed. I will just order it from somewhere else, and LCST will ship it to me within 2 weeks for cheaper. I hope. Okay, let's see. Oh no, it's not cheaper. Okay. So what we need it for? The time elsewhere. It's in stock. No, zero stock. No stock whatsoever. Yeah, we can't get this part. It's done. We are done. You know what? Industrial grade. Wait. Consumer grade, $20. Okay. I saw one piece. Consumer grade. $18.99. 2nd to 12th April. Yeah, that's just probably fast 2nd to 12th of April. Yeah, I can just try to get one of those for $20 each or $19 each. CG. Yeah, all right. So, MCP, Sonic. Nah, serial. That's not fast enough. They claim they are fast enough, but it's serial clock. The serial clock is limited to like 20 megahertz. And then if you need like 16-bit a resolution, yeah, 12-bit. That's nothing. I checked the TI components today. Manufacturer side, yeah. Manufacturer doesn't have it. If you look at the part at Analog Devices, yeah, that's what I will do. So before we even complete the ultra cluster to the point where we need a 16-bit per color component VGA card, there will be either available or we will find a different solution for that problem. But imagine HDR with 16-bit output. 16-bit analog displays will be able to resolve that. Yeah, 48-bit deepest color TM. we have to, this is like 2 to the power of 16 MCUs, so we need to have also like 2 to the power of 16 different color shades per color component. No. It's not that. It's 2 to the power of 48 colors. That's almost as many atoms there are in the universe. Quadrillions of colors. What's the number? What? Let's ask Gemini. 2 to the 48. Put that number into relation. Visualizing magnitude. Okay, it's 281 trillion. I'll colors, out of the realm of human intuition, cosmic, microscopic scale, the long game. Okay, so we would be 8 million, almost 9 million if we count each color 1 second. MAC address. All right. Biology. Your body times 8 trillion cells. All right. Okay, so that's a good paper stack. Oh, that's cool. 28 million kilometers high. What? Okay, long enough to wrap around Earth equator over 700 times or reach about 20% of the way to the sun. Okay, that's a comparison. That many colors. Trillion. A trillion is billiarde. I think this is American because that's English. Roughly the amount of sand in 140,000 Olympic-sized swimming pools. What? Turbibytes. What are turbibytes? The first time I see that. Cover the entire land. Alright, okay. What? Nice comparison. Okay, quite a lot of colors. And CRT the RAM. Okay, so I don't know how CRTs amplify the video signal, but I guess like probably the newer ones, since they increase sometimes they increase like the vertical frequency rate, so they probably buffer have a buffer for that. I don't know, but probably not. Like if you take an old CRT from the early 90s, that won't store or digitize or the RGB values that are coming in an analog value through the line. So they just amplify it, put it in a cathode ray tube. Probably the resolution of electrons that it ejects it's probably meeting that granularity. So basically we can't resolve, like it won't be enough electrons to resolve that color depth. Pure analog circuit, yeah. So it's genius. And there is no way NVIDIA cards will be able to output that. Like 16-bit of color. They can, what is 12? We have HDMI 4.1. Now what's the latest standard? What is the highest 12 bits? Color depth? Yes! Phosphor. CT phosphor stores. Yeah, basically. But we counting photons here. No, we not. That's quite a lot of photons. That electrons and photons that we eject. I don't know what the luminosity of a photon is. And what's the persist. Okay, you know what? Let's ask Gemini. LG panels are 12-bit. Yeah. What's the HDMI? Okay. A CRT tube illuminates using electrons. How many electrons do we need to excite the phosphorus to the highest brightness. It's a stupid question because everything depends on the resolution or whatever. HDMI 2.2. Yeah, good luck with HDMI. Okay. High-end monitor or bright TV. Peak beam current is a milliampere. To find the number of electrons per second, charge of a single electron coulombs. For a current of 1, blah blah blah. I don't know if the math is right, but this is the electrons. No, that can't be. That's not a lot. Breaking down to a single pixel. Oh, they are doing it. All right. Nanoseconds on a single pixel during each pass. That sounds about right. So nanoseconds, 15. It's 93 million electrons. Okay, we don't meet the resolution. Peeps, we need more. We need more, people. We need more resolution. How many bits do we need for that? That's 16 million is 24. So it's 32 million is 25, 26, 27 bits. We need 27 bits. For lower resolutions than this, we need even more. We need a 32-bit ADC to be able to meet the resolution. Okay, let's calculate. Let's take that number 93,600 million, whatever, divided by yeah, it's the but oh, you might be right if it's no, I think it's 3 tubes. You have each tube, because they send like the mask is like shifted, and you have different phosphorus there for the 3 different colors. So you have actually, okay, we can resolve down to 1400 electrons per pixel. This is the resolution that we get in the end. Okay. Ooh! Oh. Yeah, good luck with that. Brightest CRT? No, it doesn't matter. Doesn't matter if it's bright or not. We still get. You want like for the glow, like burning up. Yeah, I have only one CRT. Let's see if we can. Yeah, that will be cool. Okay, let's troll a little bit. Oh, graphics card. 12-bit. 12-bit. Now I will just add 1 bit. Just for show. Yeah, it's just noise in the end. You're running at 12-bit, really? Ah, what did I press? No, don't click stuff. All right, so peeps, if oh yeah, could oh here crazy. So if NVIDIA responds to our video with, oh, we hacked the driver to support 16-bit, then I will just add 1 additional resistor to the ADC, like a resistor ladder, and then we have 17 bits per color component, and then we win. We just one up, double the colors. With each bit that we add, double the color counts, the per component, double the levels. But I like that we will be able, if we can get that ADC. Otherwise I need to make it myself. 1400 electrons. We will count electrons, people. Yeah, my resistor ladders, I don't know what the issue is. So I show you what the problem is. I have a 16-bit resistor ladder here. Where is it? I made one myself already in the first year of my YouTube channel. The problem is they are not linear, really. I can show you the issue with the. Do I have them here? Where's my DAX? Let me check. If I might have misplaced them, but I made one already. That's 16-bit. I can show you proof. Let me check. Where is the DAC? Should be here. RF. That's the fallback. If we are not able, yeah, I took 1%. I think that wasn't good enough. Here. Oh yes, here we go. Most of the 16-bit DACs are not meant for high frequencies like that. Yeah, you need to, and probably also like, okay, here you go. Here. The PCB is etched with toner transfer. 16-bit R2R DAC. This can do the resolution. This can do the, look at that, the PCB. Oh, it's already a little bit tarnished. 12 years ago this was etched. Or is there still some paper from the toner transfer on that? Yeah, and the 8-bit DACs, they're quite good. We can plug them into a breadboard. So the 8-bit ones here, I used them I think in a synthesizer project. Boop. Can plug them in. Grünspan. Yeah. They are quite fast. I have even some Wolfson decks, I believe, somewhere. Oh no, Wolfson was ADC. I wanted to make this this microphone. Oh, I have some ADCs here. Imagine I bought like, is this analog devices? No. Let me check. I know I have some 8-bit VGA parallel to analog converters from analog devices, but they're only 8-bit. I could do should I bring them? I show you which ones I have. Since I made we can just put 2 in series. Yeah, that's the thing. Why not? I think I have no, but I didn't pay that much. They're probably like what's the frequency? Switching frequency. They are meant for like old analog graphics card and stuff. So okay, so we take that. This is the first ADC, 8-bit ADC. This is the second 8-bit ADC. Done. We just need to tune them such that we don't have a bag. Test the one from AliExpress, ITT. No, we can use the other one. Third, yeah, we can do 24. Like if we take this and use 4. Let me grab that. Okay, peeps. You enjoy this view, and I bring the ADCs that I got. I'm not sure which ones these are. 72. We won't be able to resolve that on any CRT, like 1 photon ADCs. Here. You enjoy that? This is also 16-bit resolution here. The LEDs. I use 16-bit. No, do I use 16-bit? I might not. But we are able to use 16-bit. Let me check that. I think I made a graphics card with a VGA with that specific chip that I never released. If I can find the... Is it there maybe? No. Okay, I will grab the chips and I will be back in a second here. These are my old creations. They should be in the basement. Be right back. Okay, it might not be analog devices. I found some. Not sure if that's the right ones. Because they're all in those cases here. This is the wrong one. This is the WCH USB host. That's that 8-bit MCU. Let me close that again. Yeah, that's the 559L. Use that for some projects. That was cool, a cool thing when Aaron did a lot of work on that project. Now we are checking out what kind of decks, fast decks I have here, but I think I have something else. What do I have? Lattice here. What is lattice? I think these are the substitutes. I don't have analog devices. I might have lattice. Can't read the number. Can you read the number? Hocus focus. Zip. Read the number. That might be the ADC, is not sure. Or it is here, but this looks empty. There is only one chip. That might be in. Okay, I need to check the microscope. Is it that? It doesn't sound like that's a DAC, is it? Is it a DAC? Where's the USB cable? Here. If it's lattice, then not analog devices, but Lattice did FPGAs, didn't they? Okay. Oh yes, this is the drop-in replacement for that. This one I need better. Okay, let me give you. I think there are like two types that you could purchase at that time for like, and I have still plenty old stock. Yeah, TFT. Yeah, that's certainly one deck, but I have only one piece of those. Let me turn on the camera. What? 12-bit? What is? Nah, you're kidding me. No, that's not so. Is it? What is this lattice thing? Alright, microscope. TFP, that's a classic. That's a classic display interface, I think. Oh, but they might be like with TMDS. Oh, TFP. I mean, with FPGA on the other side, 41PAP. Texas Instruments, what is this? Yeah, that. I think that's DVI. Nah, that's just a transmitter. Yeah, no, that's just a converter to TMDS. But it's a cool chip. Huh. It's nice interface. Okay, and what was the other one? Strange. But where are my analog devices? I think I had analog devices. So what is this one? I need to put places such that it won't drop on the floor. Another resistor. I have some. I know I have some because I used them. Used them for one project. So there must be. It's either this one. Okay, so let's check that one. $164 CT G 64. Lattice was bought up by something else, weren't they? What? Is it, it's not L, it's C 164 CGG. Yeah, okay, that's the one. Okay, so what is that? Obsolete. It's unobtainium, people. Oh no, it's not a transmitter. That's not right. Yeah, no, that's not the right chips. Ah, damn it. Yeah, that's not the right chip. Okay, it must be somewhere else. I'm sorry, wasted your time with those links there. Mr. Analog Video Out Tag. It is. There are like two. If I have like. I know I bought a bunch of those because I wanted to make 100 graphics card using that chips. So I just bought them. I even have like an example build already that didn't work properly, but I know I had the chips. I only can find them right now at this time. What is doing this? Where is this noise coming from? Yeah? Huh? The bag did a strange sound. Oh no, oh no, oh no, okay, I dropped a bottle of IPA and dripped down, or at least it doesn't short anything. I will be completely enclosed in fumes. You know where we can find the chip that I used? back then. Parallel transmitter. Yes, I think that's the one. Ah. Yeah, I think it's that one. Yeah, that's the one. It might be 12, not 13 at the end. But it's a similar device, yeah. I think I have that one. No, it's no, it's the HDMI transmitter. No, it was a parallel. Not. It was a DAC. What is the Easy EDA? Because I did the project on Easy EDA. Invisible flames. Yeah, there is nothing that could start the flame. Yeah, it is dripping on the floor all the time. That's why I was confused about the noise. I can at least remove it from the table because otherwise... yeah, it's dark enough here. It dripped, I think, on this bag. Yeah, on this black. Thank God I have so much trash on the floor. It dripped on a plastic bag. So we are safe, peeps. We are safe. There's not much on the floor. It's just like a little spill. Here. Now I hope you are happy now. I will find out in a second. I made the board with that in Easy EDA, so we can... Yes! 7.1. It's probably that. Okay, design online. Standard edition. Let me load my projects. Skip. Okay. Oh, here we go. You were close. Yeah. You were close. Here it is. Permission error. What? That's the ADV 7123. So this was my mini kit at onboard with audio and the chip. Okay, do I have? The new Mr. Analog Output. What? What is the Mr. Analog Output? Okay, restricted availability. Okay. All right. Let's see. Okay. I have some of those. I have like a bar at 10 bits. Wasn't that... How many bits did... Yeah, that's enough for 1 electron per bit. 24... No. Divided by 6... that's divided by 64 only. Yeah. 22 electrons. We can go down to 22 electrons per color component if we put 2 in series. 20 bits per color component. Is it even differential? It seems like it's differential, huh? At this speed. Voltage reference circuit. What? What do you mean with stupidly expensive? I saw some like for $60. Yeah, I saw them. 64. We can get the. Ah. But this isn't the chip. It's a different chip. Blank sync logic. Yeah, that's parallel. P safe, power down mode, clock. I guess I made a mistake with the clock back then. How do I did the clock? Did I send the clock with them? Because it never worked. It was something was off with that test back then. But I have those. Oh, here we go. Yeah. There it is. There is a similar one, not from Analog Devices, which is as capable. It's just a different brand. It was like you could get it for $1 back then. I know because I was researching. These were already quite rarely available. But if we can run that in series with R2R ladders. Cool thing. Alright, we might not need like this expensive ones. I mean, these are also expensive, but I own them already. Okay, so yeah, we discussed that now. This is the power. We will be able to trim it, test it, whatever. Fondue wrappers? No, it's components from LCSC. The bag is now really big. These are already the components that arrived for our build. Look at. That's 150. That's 150, I think, or 130 of the connectors. We have to solder them by hand. Look at that. If we need to get like a second board, they came in bags like these here, and probably even wrapped once more, and so everything is wrapped in plastics, like chip resistors of different values. Oh yeah, these were the longer ones that we don't need anymore. These are PCI Express times 16 connectors. So that's like $100 down the drain. Peltier, no Peltier. It's not a Peltier, it's a fan. And we have plenty of parts. Here's the load, we have the loads. Save them on, sell them on eBay. Oh, I found the other one. So this was This was the one where I decided. Here, this is the R2R resistor ladder, 8-bit, similar board VGA. Let me check, show that here. That was, look at that, never released. That was also a mini kit version. It had 3 colors plus, I think, audio was, I don't know. How did we do that? Yeah, we had the decks, the internal decks were audio. But it's only line out, so you couldn't, you could basically destroy the... No, I think I have like the caps. The caps prevented, yeah, the 2 caps prevented it from melting the internal deck. Look at that, the number here, the batch number. White boards. Very odd. I never sold those. We can look at the old stuff that I had on. Where is it? On Easy EDA. All the nice projects that I never finished. Even like the RPOE thing is there. Okay, here we go. Let's check out the old projects. Where's my? How do I get out here? Yeah, that's what we do. Then 10 bit, you will just double the bit count. Because you have like two outputs. Will it though? Yes. No. Oh no, it's not the same. We need to... Oh, how do we do it? Is it though? No, we are halving it. Oh no, it's not that easy. It's not digital. We can't put them just in series and then expect them to work like that. We need like to lower the current by to... Yeah, we would need like to... Let me just draw that. So if we have... Okay, so we have ADC1, ADC, or let's call it 0, and then we have 1. Oh, you're right. Revert. DAC 0, that's for the lowest, the bits 0 to 15. Then we need some really precision circuit here, and then we have DAC 1. Now comes the stupid logic. This is 16. Oh wait, that's... we have 10. Oh, ow! We have 10 bits, so it's 0 to 9. Sorry. Okay, we need a bigger eraser. Why is the eraser so small? Huh? What kind of eraser is that? Alright, here we go. Okay, 9. And then we have 10 to 19. Okay, so what we need to do is we erasers from Temu. We need to, how do we do it? This needs to be divided by what we will do is, let's say we have we need to emulate the circuit, okay? So voltage divider. This is ground. This is ground. This is basically 1 ohm. This is 1k ohm. And then we have what happens here? No, there needs to be like a 50 ohms resistance series as well. Oh, we need to emulate the circuit. We need to emulate the circuit. Time for sleepy. So this needs to be 1024th. So it needs like 24 as well, like here. Second resistor 24 ohms. a precision trimmed circuit. I don't know, that doesn't work like that. Ground reference? Yes, that could be done. Oh, it will still work. The parallel signals, it's really not relevant. Like for the laser. That's a cool thing. One ADC drives the ground of the other ADC. Oh no, we need to amplify that then. No, that needs to be fast as well. It doesn't work like that, does it? No. There is too big of a charge on the ground. We have like caps and everything which is smoothing it. That wouldn't work like that. We need to operate on the output signals. No, that's not working. That's like the stupid LED TVs where you have like a big LED in the background that just dims the whole screen. No, that's not working. That we need. Okay, you can think about that. You can simulate it. We can. How do we simulate again with these tools there? Short circuit and yeah, we can mix, but then we get only 1 bit more out of that. We would need like a cascade of plenty of those, like 64 of those to get the resolution of 16-bit per component. So no, yeah, we need to just adjust. Like if we have like the, let's say this one has an output like that. Let's say this is the analog. We need to zoom in. Yeah, basically. So this is DAG 1 and this is DAG 0. it only adjusts like 1024th of what the second one does. So it could work, but we have like current flowing in both directions, which is like and we don't need like we don't have like a super fast we if we take like a super fast op amp, we can compare it or something. Oops. Like put it instead of ground, we could put in like minus, I don't know. What is the tool again, the online tool for simulating the circuits? Walkway. I don't know how to use that for that. Yeah, we don't need to solve that today, peeps. It's more important to solve other stuff. This is maybe. Where's my tools? Okay, you know what? Or it has been solved somewhere, and it's stored in a huge LLM. Split two chunks, MSB tag, receives 12 bits, convert analog, blah. Passive summing, you can just add them, must be attenuated, scaled down. To combine them, output follows this logic. Yeah, that's what I drew. Okay. Yeah, but how do you combine it? The reality check. Oh no! What is this? You're trying to split bits, but better performance. No. Reality check. It looks great on paper. Two major hurdles. Resistor tolerances. Must be accurate. Yeah, but the attenuation shouldn't be that hard. Like with 1024, if we operate, okay, we lose the impedance. We need some fast. Hey, life. Claude, tell Claude give you LT-Spice file. What do I do with an LT-Spice file? Peeps, give me a link to an online tool where everything is done. Hey, Chris. Bit splitting, very blah, differential, blah. Yes. It's an op-amp circuit, so yeah, find an op-amp that's able to operate. I think we found an op-amp that is fast enough, but will it also be able to operate at this precision? Does it matter? It just needs to be the numbers on paper, and theoretically what is Voltage follower buffer between each DAG, summing resistors ensures the resistors won't load down the DAG, ruin your precision. But how do you use a voltage follower at these low voltages? That's like in 1 millivolt. What's the output of the chip? What's the voltage? If we can, yeah, even if it's 3 millivolts. The noise, peeps, the noise. Frankenduck. Nah, I don't need code. Okay, peeps, this is really too much of a hassle right now. We can experiment with that once I found the DAX. I don't know where it is. I need to check. I have differential op amp. Yes, basically that. But will the precision of the differential op amp be as high? Because you have like the op amps have noises as well. If you have like your power supply, there is no way. This is something that we need to pass to Marco Reps. He needs like to use temperature controlled output. Duck squawk duck. Yeah, a duck. That was, someone was joking about that when I used the word duck, a duck, in one of my videos. And then I picked up on that. It was like a comment in the YouTube comments. I picked up on that and then used like the duck emoji to show it every time and on screen, like coming up from below and dropping when I said that word again. I don't know if I can find that. That's a super old video. I can use resistors. Yeah, that was the video where I made them. Yeah, this is the R2R. When is it? 12 years ago. All right. And I think the video after that or something where people critiquing me about that. Yeah. Will I find it again? Yes, I still have it. It's in the basement as well. We should do, but I think it didn't survive the move. Dag. I think we had. Yes, it might have on the back an extra BCD cable input for. I used it to display. Like, we look at that. We had I drew the ADSR curve on. I used external DACs. Look at that. This is the ADSR curve. Okay, it was a little bit distorted when I played the sound. Maybe we can see the circuit. Yeah, here. This was the output X and Y. This is the audio with an Arduino Mega, and this is the X and Y. These are basically the same ones that I have here. So I probably even used the 8-bit text that so basically, yeah, and we were able like to shape the ADSR curve. Yeah, we can sustain is increased and decay, whatever, attack. This is the release. So basically I use that for basically as a display output for real-time graphics. PWM. Where did I use the DAG again? Where did I use the DAG again? I think it was later when I did that's the scope display. No, this is it might be one of those 3 videos where I duck. Organ pedals, yeah. They were too big in the beginning and I cut them shorter because and they were quite noisy. The mechanics weren't like perfect. It was quite cool since I used analog, and we talked about that before. I used analog Hall effect sensors and magnets, so I had like polyphonic aftertouch. Very crude, everything. Yeah, here, these are the magnets. Yeah, these are basically the magnets. And then bare feet, like testing stuff. Sensor array, okay. Yeah, yeah. Yeah. Yes, this is... that's the array. Gross. Oh, I can hear that. Here, the test.
In the center you can see my first approach of the multiplexer cascade. It worked, even it was not the best solution.
Lol Janko ribbon.
That's like analog multiplexers that I used.
After the sensor array was ready, I could assemble the device and test it.
How many? That was like
soldering via plastic.
So okay. Let me turn off the desktop audio again so you won't listen to yourself talking here. Yeah, it's so really cool. Anyways, yeah, DAGs and ducks. It's German, like to say I don't know. Alrighty, now we were just chit-chatting for 2 hours, and let's see if anything happened in the production file. No socks, yeah, not in that video. Didn't change anything. Solder mask still. And then this one. Yeah, still the same. Filling epoxy for 3 days. No, 2 days. I don't know. I'm not bothering anymore. I can design this one in peace. This one here. It's quite cool. The polar. This is something. The polar grids on this is so crazy. Look at that. if we grab that component and we shift it around, it will rotate basically about around the center. This is a feature if you're using that. Yeah, I hope they will be able to play some. At least they didn't complain. Yeah, let's move it back. I wanted to fix something that I saw here. Let me do that. Oh yeah, one thing that I wanted to talk about today. I think Kaspar is already in bed or probably brushing teeth again before going to bed, watching a TV. What is this PCB? This PCB? Guess what it is. It is, maybe I can show you. Okay, let's take a look at the 3D. That's like almost 50 centimeter diameter, and these are these PCI Express connectors there. You can see them. So it's a quite substantial board. And then maybe we can see that here. I should update the board. Wait, the preview. That will load. It will load for a second. Infinite improbability drive. Yeah, improbable that this will work. Come on, it's loading. It's loading. You see the bar there? Mini Cray computer. Except, what was the IOPS, the Cray IOPS, Cray 2 IOPS? It might outperform it. A clock, yes. Yeah, they will make it. It's not expensive. Probably $100. Oh no, wait. Yeah, no, it might be $300 or something. I'm not sure. Depending if I want to have it 4-layer boards or 6-layer boards. This is currently impedance matched 6-layer board, so it will be more expensive. I think it doesn't exceed their limit. It's like 60 by whatever 50. Does load finally. If it's becoming a problem, then I might be screwed. We will pivot then, make another bot that's square and put it in a square aquarium. No. The most expensive parts are the ones that are plugging in here. Flops, yeah, floating points. IOPS, I need IOPS because we don't have floating. Oh wait, we have floating points units. I'm not sure. This will have not roundabout, 2048 plus 128 FPUs. So let's cut. 115 kilowatts. Okay. Yeah, we're not using that much. 128 plus. Okay, here we go. That's the count of FPUs running at 120 megahertz. But let me check if we can find out what the multiplication takes. Okay. Thinking. Single cycle multiplication, hardware division, precision flow. Yeah, but it won't be able to like store. You probably need like 4 operations around that to run that 124. Yeah, but they're not running. They're like at one. The internal clock wasn't able to run it faster than, and I messed up. Yeah, it's not comparable. It's not like. But let's assume we have that by 100. Okay, we multiply that by 120 mega divided by 4 because we need like to put it in registers, load them, whatever. Let's say like that. So we have 65 gigaflops only from the controllers that are not the main MCUs. Just from the row controllers, we have 65 gigaflops. Sounds a lot. Is this right? 120 mega? Yeah, that sounds about right. So here you can see this has an internal FPU and these don't have. These are running at 100 megahertz. We have 32 of those. They can do an integer multiplication in one cycle. So the conversion to float and whatnot would take a while and stuff like that. So probably the power of this one is comparable like to all of these combined regarding floating points. If we use like fixed point multiplication and so on, then we will probably have like 4. But I don't think we will do yet 32 float together. No, it's yeah, you will probably need like 32 cycles to perform like a floating point multiplication on that. So in the end, it's basically this MCU will be as fast as this here. So we can just double it. Let's assume we have 100 gigaflops. What was the cray again? 160 megaflops. Okay, yeah, it outperforms a little bit the cray. Just a little bit. As the plan. Did it load already? Like the preview? Yes. That was the old preview. And this tool isn't as good as the actual. That's like these are the blades. Yeah, we need to store. I think I can reload that update selected part. I might have submitted it to server at some point, but it doesn't have anything except I think the connectors. It will now load for ages because it reloads all the 10,000 components on here. Yeah, you that will be 2 blades next to each other and 128 blades in total. And they are on order right now. Yeah, but these are only the first 4 boards. These are the boards. They are in production. There will be electronic lollipop. Yeah, here we go. That's basically it. It was hard. Hey, icon is. Yeah, this is now loading. It's generating the 3D files. Anyways, no, it is a massive number cruncher. No, said Tuna. We have 65,536 MCUs. Do you know the QVGA resolution? Are you aware of the QVGA resolution? Oh yeah, for the people who don't know how we will power it, this Corsair power supply is able to provide 3 kilowatts that we need. We will probably need around about like 2.4 kilowatts for that cluster. And then we need like another 32 boards power boards that will convert this here. This is the side view. They will be arranged in a circular way on the perimeter of the base of this cluster, and they will convert 12 to 3.3 volts. Each of those is capable of doing 30 amps, and we will have in total more or less 30 of those. 32, wait. Why not put the DC to Z? You know why? Because this DC to DC, the Murata DC to DC, is chunky. That's alright, we could still fit it. It's like 8 millimeters high. Then, if it breaks, or if I do a mistake, the manufacturing of this board, 128 of those. Imagine there is like something wrong, or it blows up or whatever, the PSU. You have like to redo all the boards. 320 by 240, that's in total 64K pixels. Now, if we have 65K MCUs, we can dedicate a single processor to calculate whatever we are rendering on 1 pixel. Imagine that. World first. Even Nvidia doesn't have that. They have like, what is the top? 30,000 pixel shaders is the most they can do with the latest graphics card, and they can't do 16-bit per color component. 20K. This will real-time ray tracing with 1 MCU per pixel. We can run some complicated distance functions. We can do a Mandelbrot zoom. Like really old school on the CRT in 20 bits per color component resolution. We can run it into like depths never seen before. No, no. There are LEDs. They can show the pixel that they are rendering. I mean, they can show that, but they have this bus here. This is like a here. Each row has a 32 megabit per second SPI bus. These have an SPI bus. These have like additional 16-bit parallel bus, the cards. The only challenge is to digest all of the data so we don't get a bottleneck here. We calculated the wait, let me dox myself. Ultra cluster. We calculated VGA here. No, that's the step. Oh, no. Power testing task course. Yeah, we calculated the data transfer. 12-bit HDR SPI bits per second. We need only at the lowest level, we have several levels here. 32, yeah, that's not true anymore. We have like 16 here. So basically that shows what is the lowest level bitrate that we need for 4K 12-bit HDR here. The lowest level bitrate transfer rate will be, we are somewhat bandwidth limited. So currently we have 16. This will be the level here. I think this is 16 now. We need 17. Yeah, that's still possible. We can do 32 megabits per second. This is 17. Oops, you can see because behind the chat. So this is but this is only 16-bit. Is 12-bit. If we do 16-bit, we need more. So probably we might get away with LED. Yeah, basically. So, but we have QVGA, so our throughput, we need only 64 for like this is 8-bit. But imagine if we have like double that, that's 100 kilobits per second on the card output. Yes. So here at this point here, for QVGA in 16-bit per color component, we only need like around about 100 kilobits per second. And then we need to digest this stuff here to achieve 94 megabits per second, which doesn't sound a lot. We can make like a 4-layer PCB. So this one here, plate base. This can be a 4-layer PCB. We don't use the 16-bit output. Wait, let me check me. Let me check me. No, wrong. Plate interface. Yeah. All right. So we don't need to use the parallel bus that's on here. We have 16 bits. We can just use the SPI, which will be fast enough, and then we need to digest it. And the digestion here is how do you do that on this massive board? Oh wait, it's not fast enough because we're using PWM. Oh, they can switch like 100 probably megabits. Yeah, each LED color component can do megabits. fiber optic. Yeah, that's too expensive. We are at scale here. 128 PCBs. Well, PCBs will cost like around $8,000 or something. So it's quite a lot. I'm scared. That's why now the first batch is only 4 boards. And then we need to digest all the SPIs from here. We have 128 SPIs. If you add $1 to the BOM of one of those interfaces, that's already $128 in the total BOM. Just imagine that. So if you try to do anything here, like add, oh yeah, we take a serializer that takes those 16 lines, so converts it to TMDS. I mean, I have them here, like the TMDS converters. We could do that, but I don't think I have 128. I'm missing a few. We could put them here and convert them to TMDS, but then you have like, what is it, 4 TMDS lines, clock and RGB, and then you need to digest those. And the solution to that issue is also in this smart sheet, level 3 here. Now is the time of Caspar. Caspar, your time has come. Tang primer 20K is this little cutie. The benefit of that, let me show it on screen. Benefit of that is, no, not that one. It's using DIMM socket, and you can connect. It has RAM, like DRAM, and you can connect directly to program them. You can connect directly the JTAG, and you can use DIMM slots, which are basically vertical. Don't have a vertical one. I think I just got them for testing. They are quite sizable. And pricey, $30 per tank primer. And if we take the SPIs, like if we take all the SPI lines, put them in parallel, just don't, like we have 4 lines. If each, yeah, wagon loads, and that's 128 times the $10. Now we are able to use only 32 PSUs instead of 128, and if we put like a $10 MC DC to DC converter on the, if we don't develop it ourselves on the PCB, then I also don't want 12 volts to be basically on the PCB that can be damaged. That's $8,000 that we can basically damage if we mess up there something. So I want to have basically the power unit somewhere else, and then only use 3.3 volts as an output. And they recommend, even on the power supply, they recommend, do I have it here? Yes, I think that's the one. No, that's not the one. Yeah, that's 4 months of work so far. So the planning, it's supposed to be submerged cooled, but the liquids are unobtainable, and it's like another $2,000 of stuff that I would need like to put into that. So we'll air cool it right now, put it like upside down. It will be air cooled from the top, because we need to dissipate like 2.4 kilowatts of power. It will be like 70, even though I run each color component on the LEDs with 1 milliamp, it will emit like 70,000 lumen. So crazy. What did they want to show here? Forgot. Oh yeah, they recommend the Zener diode here. They just recommend the Zener diode because it has like a short circuit protection. So if there is like if we put like a Zener diode of 3.5 volts or whatever, it would be able. Yeah, they don't. Did they recommend any Zener diode on the bomb here? No, don't see it. Oh wait, C23 to 26? No mount. Yeah, I don't see anything. Yeah, and that's the problem. We have only 1 centimeter between the boards. Oh, we could do right angle Dupont connectors, yeah. There's always like, it's a design choice. We put like the power on that because I know PCI Express connectors are capable of handling that much current that we need. It's like only 20 watts or something per card. Yeah, it's 20 watts per card. So that is, I distributed, we have all the power calculations on that. No. Power calculations here. Basically for that, initially it was a bigger board, but nobody was able, like JC wasn't able to process that. It made the server crash and everything. And I made it quarter the size, and then half the size worked. So now we are manufacturing half the size. And then we have, this is the maximum current in spec. It's like 400 milliamps per pin, which is totally fine for these connectors. I think they can do like 1 or 2 amps into per pin. So and these are quite okay. 400 milliamps. This is what I calculated. That's why we see now. That's why we see this here. This is the highest current path that we get. That's a total of about 60 watts. 60 watts here. 20 amps. I have no clue if that gets hot or not. It won't be covered by this is on the back side, the connectors here. On the front side, this is the back side, this copper pore. So it won't be covered by the connectors, so if there is like any heat. We could even like put on this on each layer, but I have still some signals to route here. Especially in the center, that might be an issue. Or I put the Tang nanos, Tang primers on both on this side. This will be okay because there is plenty of space for routing here. I need a continuous ground plane though. Yes, but this is not a trace. That's like a polygon pour. I use that to do basically to calculate the maximum current ratings for the traces on the main blade, and it was all fine. I think the 1 millimeter trace width was capable of doing 2 amps or something in max, which is already way too much. Like, we never want to put that much through it. But this is here, if you, let's say this is, I think 3 centimeters, yeah. Yeah, it's 30, that should be 60 amps should be possible here, and we are putting 20. But there's like the short path is here. I mean, from these pins. What did we say? Okay, it's 12 pins, 400. Yeah, that's basically 2 amps. No, well, what would I say? No, 12. Can't calc anymore. 12 times 0.4. But this is, yeah, 5 amps. 5 amps for, let's say, this width. Yeah, 5 millimeters. That's all right. It will be this board. I can do arrows on that. We can do like several versions, because that's only one board that I need to replace, not like 128. So I wanted to keep the ones that are so expensive very simple and test them before. So once I tested them, I know they will work. I can manufacture them and then fix everything else. So we have the potential for having like a 16-bit SPI powered parallel bus, and we just need to process that. And processing that is happening using level 3 as that. So what I checked is Tank Primer 20K is now talking for 3 hours. My throat is already swollen. It's today not productive stream. It's explaining stream. But I mean, we do some sparing, and maybe you have some inputs. Talking about the ADC might be something to digest for me. Yeah, so the Tank Primer 20K has 96. I counted them myself. I didn't count the GPIOs that are, we have like 1.5 volt GPIOs, so they're restricted. That's, I think, the power banks that are used also for the DRAM. That's why they're limited to 1.5. But these could be used to do like the communication in between all the FPGAs. And the Tank Primer 25K, however, has only 68 pins, but look at the price. The bigger one, I mean, we have DRAM, we have some, but it's quite substantial. It's in size, and oh, really? No, it was for the cooling that I arranged it like that, because I needed to put it in a 50 centimeter diameter tube, acrylic tube, to be able like to no, I didn't. I could place them in all in parallel. I don't know. It should look cool. And yeah, we are stuck now with that design. We can still rearrange it later. The blades are not like complaining if I put them in like in square arrangement. Yes, that's what people suggested. Spinning it to cool it. But then we need like a slip ring of 3 kilowatts. All right, so $18, and then if we want like in an individual SPI for each of the cards, we need 24. Wait, something is wrong. This is off. Uh-oh. C3, C4 divided by G2. G2, no. C. Huh? Oh, yeah. Wait. So, we can cover with one tongue primer, we can cover basically 24 SPIs, completely parallel, independent. If we do like sequential reading from the data, which we can do, induction powered, yes, a Tesla coil on the top. Yeah, we can handle like 24 SPIs in parallel on one tongue primer. So this one will do 24 SPIs. We have 128. The 25 thingy will do 17, and this is the size of the tongue primer 25. Look at that cutie. The only issue is if I put it on the first board, Jacob's ladder, yeah. I built one before. There's also a video on that. So I think I might go with those because I don't get space issue. And they are a little bit cheaper. And they can handle, I don't know. There is like a MIPI interface. No, but I think you can use a P mode for that. Oh shit. We have other Tang. This is the Tang Nano 20K. That's that has like HDMI, even with sound support. So this is I think this is the bare one, but there is another one with more complex stuff on it. Yes, I will just, you know what I will do? I will do the VGA, and then I will use just the Tang, either the Tang Nano 9K, this one here, or the Tang Nano 20K, just to ingest the parallel bits, like the 10 parallel bits, and then put them out. The cluster output data rate. Yeah, that's the issue. We don't know yet. The more we throw in like money, the faster it will be. For now, I will just keep it simple, so I have like a first version, and then we will just increase the higher levels to not be the bottleneck anymore. The potential is high. We can do we can probably clock 64 megabytes per second from each card, 120 times. That's the maximum theoretical bandwidth when using with the design of the cards that we have right now. So what is it again? 64 megabytes. So this is times yeah. So the theoretical maximum bandwidth is only 8 gigabytes per second. That times 8 is basically, yeah, cute. It hunts us, huh? Yeah, unfortunately only. Yeah, sorry about that. We probably even can. high speed data on the shortest buffer. Yeah, I know. We kept it that way. That's like it's arranged. Everything is arranged like that. Each bus is a maximum. Currently, it's now 20 centimeters is the longest bus, which is a stretch. I know. But that's only 32 megabits per second. Yeah, megabits bandwidth there. It's fast enough, I believe. I'm not sure. We'll see. We'll see. What we need is QVGA resolution at 16 megabits per color, 48 bits or 90 bits, whatever we use there. No. That's the theoretical limit, but it's quite expensive if you look at that. Okay, so we need, for SPI only, we need 8 of the Tang Nanos, whatever, the small ones, which is already this time $850 here. Okay, so $150. If we want total parallel and total cards, so SPI and parallel is 38 of the MC. I don't think we need that actually. If we can do 32, if we can squeeze like reduce like one line or something, we probably we'll get away with 32. That's basically the same count as the connectors on the PCB. So each of the connector will have like this little thing 2 times. So if we put like, here is enough space. What is this here? Yeah, 30 millimeters. That is 23. So we can put like 2 of those here, like 2 of those here to digest all the data. But this is like a stretch, and we need like impedance matched. We can probably get away with like 4-layer board. Not sure, because that's quite dense. Okay, this is all grounds. Yeah, 4-layer board might work. But then the core needs to be close. We need to like a better stack up for that. Or strip line design. Uninterrupted ground. Yeah, this will be tight here. Look at that. Okay, these are grounds. That's convenient. Let me check. Let's wire this one. And then what is the... Oh yeah. That's the width, 1.27. That's the impedance matched with... Yeah, that's plenty. We can fit all the lines there. And there is enough space. There is enough space here. We have like several layers. Right now it's a 6-layer design. I probably will go with 4 layers because this impedance matched 6-layer design. What I can do as a starter, which will work for this project, for the video, for whatever sake we do here, is put just a DuPont 4-pin DuPont thing here, or 5-pin if we want the ground also, return path. Put here, right next to the SPI, MISO MOSI SCK CS line. Yeah, we can put it on here, like right next to it, and just wire it wire it to one PCB that digested it all in some way or form, just to have something. And if it's a 4-layer board, that will be plenty enough. Even like a 2-layer board could be sufficient in that case. So I don't know. I can check that if we do order now, and then let's see what 50, no, it's 45 by 450 by 450 board. Okay, let's see 4-layer design. Oh, $200. Okay. Ay. Yeah, it's 5 boards. All right. That's without all the shenanigans. What if we do it? Yeah, no, isn't worth it. 6-layer, $400. So we might want to start with something that will work. Oh, yeah, I don't know. If we want an impedance stack up, let's say we want something like that. Not sure if that's the right one. Yeah, it doesn't cost much more. And we want smaller vias here. We don't need, actually we don't. What problem? With what? With the cluster, or with the calculation of the board cost here right now? We can get a coupon for $17. I can get like the next board, since this is not like an order of like $8,000 or something. I can get those sponsored to a follow-up video by JAC. They would pay that. And it's way easier. And on interface. Oh yeah, purple. Yeah, it is purple. You're right. It adds a little bit of more cost, but it will be purple like the other ones. The other ones that I ordered are also purple. That's the only other solder mask that is capable of the precision that we might need. Hassel. Oh no. Enic. $300 already. Ay. What's the most expensive stack up? Yes, I don't care. $50 more. Yeah. Oh, yeah. Outer copper weight. Ooh. Huh? That isn't like more expensive, is it? No, the impedance turned off. Specify stack up. No. So we get away. Look at that. If we calculate like that, this calculation, the SPI between, we have like one SPI per card, and we have 128 cards. How it will be supported mechanically? It will stand on something. This is something, I don't know. We will just use spray foam to put it in place. 3D print a nice case, whatever. Use hot glue. Something like that. I need to print. I mean, that will be some work still left. Oh, damn it. This is like 3 weeks of hard work still. Yeah, there will be mounting holes. The blades have already that. If you look closely, because they are not. Yeah, oh yeah, this is the latest design. Somehow that doesn't like restore the color correctly. If you look here, since I needed to put the connectors to the outer side of the board, because otherwise they would be too close together here. I added like 2 mounting holes for 3D printed stuff. Of course, the baseboard needs like some mounting holes, so we can put like 3D printed brackets to support the PCBs, and of course to support the whole structure, like this board. I don't know, boards like that of that size, they're quite sturdy. I mean, this is like the blades here. This is like an old blade. That's 20 centimeters. Yeah, that's sturdy enough to hold several kilograms. If we put like only few standoffs here in the center, and we need to see where the space is. This doesn't weigh a lot. 250, 300 grams. This is 256 MCUs. We will have 512, which are small QFNs. They will be smaller. Wait. This here is 160 MCUs. I don't know, but these are like 1mm boards. Yeah, I know. It's like these are the QFN package that similar to what I will use. So it's somewhere in between those two. It will be several kilograms heavy. We have some mounting holes there, of course. I mean, we can always 3D print a bracket that supports it everywhere here where there is space, so no worries. Yeah, you can put 20 kilograms on a 3D printed base of 50 centimeter diameter. Don't worry too much about stuff like that. We can always put it in 0G. At this point, yeah, at this point, you know what weighs more? The power supply. This thing weighs more. This is like 5 kilograms already, and there is like so much copper. I will make I think a wooden black box on the bottom as a base, and then put 3D printed brackets, like the circular shape will sit on top of that, because like I need some space down there to handle everything. Anyways. No, the hole in the middle is for something else. I will show you that usually yeah. No, this is shit. So the rotation. All right, here. So this is arranged like, usually that would be in a container submerged with cooling, and they're not in yet, but there are like outlets here between this connector 1 centimeter, and this is the inlet for the flow of the coolant. And the issue is like it's narrow. It's 1 millimeter between the boards only, in the center. That's everything is calculated here. Don't worry. It's like I calculated every aspect of this board for 4 months. I mean, it might be still errors in Here will be the power connectors on this side. Yeah, that's the back side of this board, and then we will that will be, since I will be air cooling it from the top, not water cooling it from, or like submerged cooling it. The problem is the coolants are toxic, like PFAS, whatever, and circulation, the pumps and everything. That's a lot of effort, and now we need some results. So I will just turn it around, put it on the base. The base will be 3D printed. Then we will have XT60 here. There will be 32 boards that are arranged. The 12 volt to 3.3 volts will be arranged at the perimeter of this whole structure, and on the bottom there will be the PC power supply that is connected to, like, with a lot of cables connected to each of these 32 boards, and they will convert it and supply each of the XT60 connectors, which are of this type here, will carry 20 amps of current. That's it. There will be more because we have, this is only for the core voltage for the little MCUs. There will be more for the LEDs, which is a fraction of that, and for the controller MCUs, which is even a smaller fraction of that. So the main current path, the continuous current of what? Of the DC to DC converter. 30 amps. The connector is 60 amps. The issue is rather the cables. No, it isn't. Okay, yeah. And so tell me if you know. We are using 1/3 of that. At most. You can now save me from making a big mistake by telling me. The issue is, like, the gauge wire. I use 12 gauge wire. Yeah, XT30, but this is XT60. They are so beefy. The diameter of the connectors, 4 millimeters. No, 3.79 is the pin. The length of the pin is like 5 millimeters. Okay. The issue will be the cables, but I can replace them if they get too warm. Yeah, I use AMAS says 30 amps. Yeah. Ground loop problems. Why that? Uh-oh. Wagon loads. What are you referring to? They will have all a common ground. Peak burst is like 180. Y rated, many consider 40 to 50 amps. 60 amps is the maximum recommended sustained current, they say. If you use 60 amps continuous, they rather recommend XT90, which I have also here. But I considered XT30, but they're not very common. Multiple ground paths with okay, wagon loads. Elaborate, please. What will be the issue? The ground paths will be able to support more current, at least more current than the power paths. So we have always, like, this is all ground here. Do you see that? This is where the current is going, and this is where the ground is returning, and they share all the same ground. It's not like two different power supplies. We get all from one 3 kilowatt power supply, so they have a common ground everywhere, except like there will be some oscillation or ringing, or I don't know how that could happen. Ground loops are more or less like than 50 hertz or something. That shouldn't affect like the crystals or anything. They are running at 32 megahertz. Like if you have, I mean, isn't that like the ground loops that you get if you connect your audio cable to another device? You get like the 50 hertz loop. But this is all the same ground. It's coming from this power supply, all same ground. It will go to the DC to DC converters. The DC to DC converters will pass this ground basically to the main board. Also the main board will be also connected through another, because I need like 3.3 volts supply that I will take probably directly from the power supply. So there is also like this ground. So the reference design of our, I'm done with talking. But I really want to discuss every single aspect of that. That's all right. The fewer mistakes, like the mistakes get more and more expensive right now. Induction loops. Ground leads act as induction loops. How? We don't have AC. That's all direct current. Oh, you mean like we have spikes or something? It's some filtering or like when discharging. So that's the thing that I considered. Yeah. Okay. So no, compute is like noise. Compute isn't the thing. They will like always, like the difference in, if I would let them all compute the same thing, we might see some difference there, but they're all calculating an individual pixel or calculating individual hash. That's like random noise. This is like better than this, like 65,000 MCUs that do different things at the same time. It's like a good current distribution, unless they're like doing the same thing. My consideration, because I learned that lesson from the LED wall 3, which when I did a big mistake, I don't know if you remember the streams where we killed basically the LEDs. Yeah, we won't coil them up. If you're worried about that, let's not coil them up. They will be just straight. And then I learned the lesson that when initially all the LED wall was like white, we had the current like in rush, and the DC to DC converters overcompensated and killed LEDs. Every single time I turned it on, some LEDs died. All right, so I learned that mistake from that. Just changing from like fading in the LEDs solved this issue. Yeah, and this is what I'm also considering in this design. That's why I have the blades here. Never this rotation, I never learn it. Never learn how to rotate here. Ah, here it is, okay. So, the blades, they have individual power lines per columns. We have like four columns of MCUs and four columns of for LEDs. We can power them up individually on the design of the blades. The main board doesn't support that. It just supplies 4 cards at the same time. But we could, if we like, we could distribute that current power rise time. Not sure. Can check the data sheet, but I don't power them all on at the same time. So that's why where is it again? My data sheet here. Oh wait, let's show it here first. Base. Okay, so we have like a separate power supply for 4 blades. Only the MCUs, no LEDs. LEDs, they have like a PWM switching noise. They will have also their own MCU DC to DC converters. But all these power supplies will have an individual, because I don't want also like all this current in rush from the Corsair power supply. That will just shut down if I try to charge all the DC to DC converters at once. So this is where we get our oh, this might be the wrong thing. Yeah, this is the wrong data sheet. They have like an enable pin. So I'm able to, no, that's the wrong data sheet, forget it. I'm able to basically power up 4 cards at the same time without LEDs, just trying to get them on, continue with the next ones. So it will be just like, imagine if we turn it on, it will just power up like in a circular way. Once it's powered up, we can turn on the LEDs in a circular way. And then we will have like the maximum constant current flowing. But we give it some time basically to power up. Yeah, so we can control that for, I think, I hope it doesn't shut down. We will find out. I will get the DC to DC converters. That's like the main power supply. We can control the load there by just turning on the DC to DC converters individually in a sequential manner, and then from there I will get the DC to DC converters even this week from Mauser, so we can test that with the actual load. No, the blades don't control the power-up sequence. The power-up sequence is controlled externally. The blades only receive power. So what we can do is we can supply power. This is something, I mean, I just kept the possibility there. If you look at the connectors here, we have yeah, that's not much. 100 nanofarads per MCU. That's really it's really nothing. They recommend more if you use like the onboard DC to DC converter. All the little MCUs have that, but that's only an LDO. So not wasting that power. We will supply the right power to them and drive them even at a lower voltage than 3.3 volts eventually. But I need to trim that and see how well they perform at lower voltages. So we have an individual power line for core voltage of the controlling MCU. So these ones here, this one has an individual power line for I/O and core voltage, and these here have an individual power line for I/O and core voltage by hardware. And it will be just like an FPGA or an MCU that does that in the end. We need to figure out how to do that. There is like this, we could do it in hardware by the power OK like pin, like it's described in relays. Clong, 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 clong. And then we have high voltage spikes on each of the relays. Nah, not using relays here. We could use like solid state relays. Shift register. Yeah. Schütze. Yeah, I have some. I have one. I have some for like in my main switching. They're switching. Oh wait. I think the biggest one switches 63 Schütz and relays. It's the same. They're just beefier. They're made for switching the high currents. Schütz is like the ones that I have there. I would just take a picture. Is 63 amps. That switches on the heating. $400. Oh. Here. 63 amps at 400 volts AC. Yeah, that makes a sound. I have also a burnt one. The old one burned up. I can show you the parts. That was making some humming noises. But I believe this one wasn't rated for, that was only 40 amps. Yeah. That's the coil that was inside. And here are the contacts. Yeah, it was quite crusty old one. And I think, where is it? How does it work? Yeah, it fell apart basically. When I removed it, it was not performing anymore. We had like this 50 hertz. Here's one of the plates. I think, is it that way? I don't know. Yeah, but it's basically burned up. Charge controller, yeah, that can do stuff like that. I have some solid state DC to DC solid state relays, but I won't use that. I mean, the DC to DC converter can do that on their own. I'm now done with talking. Any other advice? The next time we see us, I will just commit it to another expense of hundreds of dollars. Now it's getting really expensive. Pizza time. Yeah, not for me. I had like 2 burgers today already. All right, peeps. We talked. Let's sum up. We talked about the ADCs. That was nice. I showed off the baseboard design. Oh, DAX. About the DAX, or how I like to say it, about the ducks. Then this will be a challenge to place those. If I want, like, I'm not sure if I want to already, if this is costing like $300 per try, I might want to place them already, at least the footprint for those on top of that, not only like a stupid wire connector. Yeah, I need to sleep over that, how I will continue. I will probably start with yeah, that's the plan. We're gonna. Oh, I'm tired. That's like controlling a sequence like that isn't an issue. That's the least of our issues. It's the commitment to a hardware design that is the hardest part here about this project. Once committed, and then, I mean, I have some room for error, but every error costs me like hundreds of bucks right now. This scale of this project is like neck breaking. Everything that I spend on this, more than it should cost or whatever, comes from my own pocket in the end. I don't know if the money would even suffice. Probably in the end I can do 128 boards, and can only afford like 64, and it will be a bummer. So every second slot will not be populated anymore. No, bitluni, what have you done? Or if I have to botch thousands of cores, better cooling, yes. But worse light performance. Alright, peeps. I can't talk anymore. My voice hurts already. It was a nice stream. I have some input for thoughts. Thank you very much. The DAX. That will be if we ever happen to build like the VGA output, that means that everything before have worked in some way or form, because we can receive a video signal that's rendered. Yeah, the ducks in a row. Quack, 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 quack. Yeah. Oh, high speed 16 bits. Yeah. Imagine that. We are running like the full HDMI 2.2 spec on a VGA monitor. Currently the only way of displaying this color fidelity is like analog circuits and electrons. What was it? 14,000 electrons? We can count them. Maybe a little bit more if we take a bigger CRT. Maybe less if we take a smaller one. Night night everyone. I'm exhausted now. This will take to continue tomorrow, and then let's hope for the best. Yeah, sensitive. Yeah, certainly. Bye bye. Good night everyone. Have a nice sleep.